My name is Muhammad Haziq bin Muhtaramizi. I'm going to present our slab. This is our first slab. For the GK, we use 1.5 kN meter square. For the QK, 1.5 kN per meter square. And then for the FCK, 25 Newton mm square. FYK, 500 Newton mm square. And for the unit weight of concrete, 25 kN mm cube. For the diameter bar, we assume 12 mm. For the slab thickness, we try 150 mm, and this is the two-way slab. For the design action, we get 9.34 kN meter square. For analysis, based on table 7.3, our slab is on case 4, and for the short span, MS1, 4.2 kN meter per meter, and MSX2, 5.7 kN meter per meter. And then for the long span, MSY1, 3.1 kN meter per meter, and then MSY2, 4.0 kN meter per meter. Next, main reinforcement. For the DY, we get 114.0 mm, and for the DY, 102.0 mm. For the S min, 148 mm square per meter. And then for AS max, 6000 mm square per meter. And for the secondary bar, we use H12 400, which is 283 mm square per meter. For the short span, which is mid span MSX, 4.2 kN meter per meter. For the AS, we get 19 millimeter square per meter. And for the support MSX, which is 5.7 kN meter per meter, for the AS we get 120 mm square per meter. Both we use H12 400. Next, for the long span, we go to the mid span MSY, 3.1 kN meter per meter. For the AS, we get 73 mm square per meter. And for the support MSY, 1.0 kN meter per meter. For the AS, we get 94 mm square per meter. Both of these we use H12 400. Next, we go to shear. After referring the table 7.4, for the calculation for VSX1, we get 13.6 kN per meter. For VSX2, 9.0 kN per meter. For the VSY1, 11.6 kN per meter. For the VSY2, 7.5 kN per meter. This is the check-in. For the BRDC, we get more than PED, and the result is okay. For the deflection, I per D actual is less than I per D allowable, and the result also okay. Next, we go to the cracking. For the maximum bar spacing, we use 400, which is smaller than S-max slabs. And for the secondary bar, maximum bar spacing, we also use 400, smaller than S-max slabs, and both of this is okay. This is the detailing for our first slab. This is our second slab. For the GK, we use 1.5 kN per meter square exclusive weight. For the QK, 1.5 kN per meter square. Next, for the FCK, 25 Newton per mm square. FYK, 500 Newton per meter square. For the unit weight of concrete, 25 kN per millimeter cube. For the diameter bar, we assume 12 mm. And for the slab thickness, we use 150 mm. It is a two-way slab. For the design action, we get 9.34 kN per meter square. And this is the analysis. After referring the table 7.3, we get that our slab is on case 4. And for the MSX1, we get 5.5 kN meter per meter. And MSX2, we get 4.1 kN meter per meter. For the MSY1, we get 2.9 kN meter per meter. And for the MSY2, we get 3.8 kN meter per meter. Now we go to the main reinforcement. For the DX, we get 114 mm. For the DY, 102 millimeter. For the AS main, we get 148 millimeter square per meter, and for the AS max 6000 millimeter square per meter. For the secondary bar, we use H12 400, which is 283 millimeter square per meter. And then for the short span, start with the mid span MXX. AS we get 116 millimeter square per meter. For the support MSX, for the AS we get 87 millimeter square per meter. And both of these we use H12 and 400 bar. And for the long span, mid span MSY, for the AS we get 68 millimeter square per meter. For the support MSY, we get 90 millimeter square per meter, and both of these we use H12 and 400 bar. This is here. For the frequent table 7.4, for the calculation BSX1 we get 13.2 kN per meter, BSX2 8.7 kN per meter. For the BSY1 we get 11.2 kN per meter. For the BSY2 7.3 kN per meter. Now we go to the checking. So for the answer, PRDC we get more than PED, so the result is okay. For the deflection, I per D actual is less than I per D allowable, and the result also okay. For the cracking, first main bar, for the max bar spacing we use 400, which is less than S max labs. And for the secondary bar, maximum bar spacing we use 400 and which is less than S max labs, and the result is okay. This is the detailing for our second step. Now I am going to present the brace frame. For the dimension, slab thickness is 150 mm, size beam 250 times to 500 mm. For the column size, 250 times to 350 mm. For the total GK, we get 5 kN per meter square. And for the total QK, we get 4.5 kN per meter square. And all the cases are stated on the diagram. Next, load and beam. We go to the span one. For the GK, we get 15.77 kN per meter. For the QK, 12.23 kN per meter. Maximum load, 39.63 kN per meter. For the minimum load, 21.29 kN per meter. We go to span 2. For the GK, 12.72 kN per meter. For the QK, 9.48 kN per meter. For the maximum load, 31.38 kN per meter. And then the minimum load, 17.17 kN per meter. For the span 3, GK 13.79 kN per meter. For the QK 10.44 kN per meter. For the maximum load 24.27 kN per meter. For the minimum load 18.61 kN per meter. And this is the data. All the answers below are the result for the distribution factor for each joint. This is the shear force and bending moment diagram for case 1 and case 2. Next, shear force and bending moment diagram for case 3 and case 4. These are the shear force and bending moment envelope for all cases.
Assalamualaikum warahmatullahi wabarakatuh. I will present about our arm brace frame, which is the calculation of wind loads. So this is the specification, which is the location is at zone 2, which is Dungon, and terrain is suburban terrain for all directions. The topography is ground slope less than 1 in 20 for greater than 5 km in all directions. Construction is reinforced concrete. Sway frequencies is 0.2 Hz. Mood shape is equal to 1, and the average building density is 100 kg per meter cubed. So the site elevation, we get the height of the building is 15.9 meter, D 20 meter, and B is 10 meter. Next is for the design wind pressure, which is this is the simplified out calculation for this calculation. So we need to find P. And to find P, we need to find V dash first, which is 33.60. 4 meter per seconds. And CFIG is the aerodynamic shape factor. We take mean watt is 0.8, d watt negative 0.3. And for C divided N, we get 1.584. So based on the previous calculation, we can get the P value for the wind watt and the lee watt. So we minus it to get the total P. So we can get the P value for each height of the buildings. Next, for the design wind load for each flow level, we use formula 0.75 times WK, which is total wind pressure times the context area. And we get the design wind load for each level. And then we find the center of the gravity of the structure. And we can find the distance from centroid, and lastly, the column axial load. Next, we need to find the P value and H value for each floor, which is we use axial force in columns, and then we can determine the P value for this K level. Next, we need to calculate the shear force in beams and columns. Firstly, we need to consider the subframe to the left, and we can find the F value and the H value. And then after finish for the K level, we need to continue to the another level to calculate the F and H value. So this is the diagram for shear force in beam and columns based on the calculations. Then we can sketch the bending moment in beams and columns based on the calculation for the shear in beams and columns before. This is for analysis of subframe for vertical load, and firstly we get the design load for the frame from the previous calculation, and then we can calculate the phase and moment for MAB and MBA, which is 40.4 kN. For MBC and MCB, we get 28.7 kN, and for MCD and MBC, we get 25.2 kN. Next, we need to determine the shear force, and for VAB, we get 57.66 kN, for VBA 70.02 kN, for VBC 56.92 kN, VCB 50.6 kN, and VCD 56.67 kN, and VDC equal to 44.13 kN. So we can sketch the shear force and bending moment diagram. For the last part, we can combine the vertical load and the wind load. After that, we can sketch the shear force and bending moment diagram for the combination of vertical and wind load.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So for the calculation design for column, so we need to calculate first the load from slab to beam and go to column. So we choose the column B13. The specification is finishes sinister base 1.5 kN m square, density of concrete 25 kN m square. The slab thickness is 150 mm, the size beam 250 500. So the column size is 250 350 mm. Okay, for the calculation load distribution from slab to beam, so we have 4 slab involved for the point column that we choose. So the first slab is 2 to 3 A B1, 3 4 A1 to B1, 2A 3 to B1C, and the last is 3 to 4A B1C. So from the load go to beam, we get the GK for span B1 2 to 3. The GK is 12.3, the QK is 1. So for the span 3A1 to B1, the GK is 15.2 and QK is 3.25. For the span B1 to 3 to 4, GK is 12.42 and QK is 2.65. And the span for 3 B1C, we get GK is 91 and the variable load is 71.7. Okay, for the axial force for column that we choose, the front beam is 1.55 meter, the back is 1.36 meter, and the left is 3.34 meter, and the right is 2.42. So from that, we need to calculate the load distribution for the 4-story for our building. So from roof to ground floor, it's the same because the long of the column is same. Also, we need to calculate the NED. So for the roof to third floor is 100 kilonewton. Third floor to second floor is 200 kilonewton. And the third is second floor to first floor is 300 kilonewton, and the first floor to ground floor is 400 kilonewton, and ground floor to footing is 455 kilonewton. It's more because the long of the column stump is just 1.5 meter. From the first calculation, we got this diagram. So we choose the third floor for our building. From that, we need to define the slender or non-slender. So the result for our calculation is non-slender about z-axis and also non-slender about y-axis. Okay, for result of non-slender about both axes, so we class is a short brace column. So LOZ and LOY that we calculate from the slender or non-slender calculation, we got 1.5 meter. So from the chart, we got a 0 because to define the reinforce, we got 0 from the chart because maybe the long of the distance of the beam is too short. So we use AS min and AS max to define the reinforce. So the total of reinforced area is 2,592. So that's all from me. Thank you.
Assalamualaikum. My name is Mama Aiman. Calculation for column. First, we need to calculate the load from slab to beam, and the beam will transfer to column. We choose column C to A. The specification is finishes 1.5 km square, density of concrete 25 km square, dimension slab thickness 150 mm, size beam 250 times 500 mm, column size 250 times 350 mm. This is the load distribution of the column. For span 2A, A3 to D, GK is 13.5 kN per meter, QK 2.9 kN per meter, span 2A, C to D, GK 17.3 kN per meter, QK 4.1 kN per meter. For span C, 1 to 2A, GK 21.9 kN per meter, QK 5.4 kN per meter. The last one is span C, 2A to 3, GK 14.1, QK 3.1 kN per meter. This is the axial force for our column. For L1Y 2.86 meter, L2Y 3 meter, L1Z 2.37 meter, and last one L2Z 3.73 meter. For the maximum load, for W1Z 23 kN meter, W2Z 30 kN meter, W1Y 37.3 kN meter, and the last one is W2Y 23.7 meter. For the NED, which is the third floor to second floor, that is 370 kN. So this is where we choose the slender or no slender for our column. The result is the Z and Y axis both is the non-slender column. Design of non-slender about both axis. The specification is class short brace column. For the both of we get LOZ and LY is equal to 1.5 meter. For the design reinforcement, we use AS min equal to 175 mm square, AS max 3,500 mm square. and we use 4H25 and 2H20 is equal to 2,592 millimeter square. That's all from.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hakim Asli. Okay, I will show our foundation design, which is pad footing. Okay, for the specification, area is 495 kilonewton, moment 4 kilonewton meter, design life 50 year, and exposure classes at C3. For the material, we use concrete FCK 25 Newton mn square, FYK 500 Newton mn square. For unit weight of RC, 25 kilonewton per meter. And lastly, soil bearing capacity is 150 kilonewton meter square. Okay, for area of footing required 2.59 meter square. For the size, we try 3.75 meter square. The size is okay. For the reinforcement, DS is 909 mm. For DY, 597 mm. For the longitudinal bar, bending moment 160 kN meter. For the AS required is 490 mm square. We use 5H12. The area is 566 mm square. For transverse bar, bending moment is 64 kN meter. AS required is 261 mm square. We use 3H12. For the maximum and minimum reinforcement area, AS max is 2248 mm square and AS max is 65,000 mm square. For design shear resistance, VED is 94 kN and VRDC is 350 kN. VRDC is bigger than VED, is okay. For punching shear, VED is negative 0.06 Newton mm square and VRDC is 0.35 Newton mm square, is okay. For the cracking, maximum allowable is bar spacing is 200 mm. Maximum bar spacing 1 is 70.3 mm, less than 200 is okay. Okay, lastly, maximum bar spacing 2 is 89.1 mm, less than 200 is okay. This is our detailing for pad footing. Next, design pile cap. The specification are and ultimate is 921 kilonewton and value is 2 kilonewton meter. FCK is 25, FYK 500, RC pi 600 kilonewton, safety factor 1.4. We assume bar 12 mm. For size of pile cap, service load is 658 kilonewton. Number of pile required is 2. Width 1.5 meter, L 2.4 meter, and depth 1.1 meter. And lastly, self weight is 99 kilonewton. For the main reinforcement, longitudinal bar bending moment is 669 kilonewton meter. For the AS required 1588 mm square. We use 50H12. The area provided is 1697 mm square. For the AS min is 2039 mm square and AS max is 66,000 mm square. For the main reinforcement, transverse bar, bending moment is 449 kN meter. AS required is 1079 mm square. We use 10H12. The area provided is 1131 mm square. For the maximum and minimum, AS min is 3223 mm square and AS max is 705,600 mm square. For the design shear resistance, VED is 30 kN and VRDC is 45.9 kN. VRDC is bigger than VED, is okay. For punching shear, no punching shear is checking is necessary, is okay. For the cracking, maximum allowable bar spacing is 200 mm. For maximum bar spacing 1 is 96 mm less than 200 is okay. Lastly, maximum bar spacing 2 is 132 mm less than 200 is okay. This is our detailing for pie cap.